Hi, in this video we're going to finish our discussion of 12.4 cross products. Specifically, we're going to talk about the applications of the cross product. So for instance, part 1. The first application we're going to talk about. We can have two vectors that aren't parallel can define a parallelogram. Right? If we have a vector going off in that direction, u, and a vector going off in this direction, v, then what you might be able to talk about is if I made another one over here and another one over here, there we have a parallelogram. You might remember that the area of a parallelogram is the base times the height. Now the base of this one is clear. That would be the size of v. The length of the v would be the base. And how do we find the height of a parallelogram like this? We would drop something down that was perpendicular. And then this, if I knew the angle between the two vectors was theta, that blue line would be the length of u times the sine of theta. Ooh, right? That should speak to you. If it doesn't, all I'm saying is the sine of theta should be that blue divided by the hypotenuse. And then the blue side would have to be the u, the magnitude of the hypotenuse, times the sine. I forgot an arrow there. Be careful. So the height there is the magnitude of u sine theta. I'm going to highlight this really quick. That dot is not a dot product. That's how we write, multiplication back in the good old times. Sometimes it depends on the context. I'm not going to re-record this. I'm just going to say it would have been better if I put parentheses there. Okay? Anyway, you might remember this formula from the very last video. That is the size of their cross product. V cross u. Once you take the size, it shouldn't really matter what order there is anymore, because the order was just off by a sign. So that's one formula for finding the area of a parallelogram. If they give you two vectors and they say find the area of the parallelogram, the cross product is telling you how big is that area. Now you might not believe this, but this is going to come into really big play later in this course. The area of one of these parallelograms is the size of the cross product between the two vectors. What about the area of a triangle? So again, the picture here would be u, v, and there's always a triangle that could complete this. Well, a triangle is always 1/2 of a parallelogram. So the area of the triangle in terms of vector speak is 1/2 the size of their cross product. Okay, and that's really all there is to these two formulas. Just know that the cross product is kind of telling you the area between two vectors, or the area described by the parallelogram between the two vectors. And again, it's the size. The size of the cross product is telling you how big the area is. The direction was given by the right-hand rule. This is a nice finishing touch to the last video. Let's do an example. Find area of triangle PQR given the following coordinates. P will be at 1, -1, 2. Q will be at 2, 3, 1. and R will be at -2, 3, -1. Okay, hope that's clear. So, this is a bit of a throwback. You could try to graph them, you could do a whole lot of work. That's not the right idea. You could pause the video right now and try it if you feel like you have a good idea. If not, here I go. We have 3 coordinates. Can you use these coordinates to give me 2 vectors with a common point? This should sound somewhat familiar. Specifically, can I find PQ and PR? PQ, transforming the coordinates into a position vector, we would subtract in the right order, and I would get 1, 4, -1. We're subtracting the Q coordinates minus the P coordinates. Try PR, see what you get. For me, I'm getting -3, 4, -3 again. Sure. Could you have used these other coordinates? Sure. Could you have gone from Q to P and then Q to R? Yes. R to Q and R to P? Yes. Will not really matter. Then what we're going to do is the area is 1/2 the size of PQ cross product with PR. 1/2, and then we're going to do, I guess I'll do the cross product down here just to be clear. PQ cross PR. I, J, K, always in the top. 1 for -1 for me. -3 for -3 for that third row. Go ahead, try to compute this right now. Pause the video, give it your best shot. 3, 2, 1. I'm getting -12 plus 4 I minus -3 minus 3 J plus 4 minus 12, no, plus 12, 16 K. Oh, sorry, I didn't know why I changed format. Fine, if I can do it the nice way. 4 plus 12 K. You should train yourself to try to do it mentally if you want to be fast. I care much more that you're getting it right, though. If you want to practice your mental math, I mean, I don't know. Part of me thinks I'm just going to have to re-record this section because I made a mistake somewhere. So I have -8I plus 6J plus 16K. Okay, so the magnitude of that big vector is a pretty big sight to behold. We're talking about the square root of 64 plus 36 plus 256, which is, of course, 100 plus 256, or 1/2 times the square root of 356. This is approximately 9.434 units. So let's do another example. So why don't you try this one? So given P 146, Q at -2, 5, negative 1, and r at 1, negative 1, 1, two things we're going to ask you to do. Find a vector perpendicular to the plane containing P, Q, and R. And then B, find the area of triangle PQR. Please don't skip A. If you can't do B, if you can't do A, watch that solution first. I feel like many people are eager to do B, but right now, A should be easy for you also. Here I go with A. The idea is I have P, I have Q, and I have R, and effectively what we're getting is some sort of plane that would contain those 3 points. Those 3 points lie on some rectangular sheet of paper that's floating in space. Okay? And we want to find a vector perpendicular to that plane. What I'm going to do is I'm going to look at vector 1, vector 2, and we can get out of that plane by doing what? Well, it's the cross product section, ain't it? So we're going to find PQ, one vector, and PR. Take a second to find both of these. PQ should be -3, 1, -7. And PR should be 0, careful with that, -5, -5. So one more time, the strategy is to get out of the plane by doing PQ cross product with PR. Right now, try to write down the determinant. 3, 2, 1. Pause the video if you had to. I, J, K. I really hope you got that. -3, 1, -7, 0, -5, -5. And what does that give me? Try it out right now. Make sure you're checking the I, the J, and the K component. Pause the video if you have to. 3, 2, 1. In the I direction, -5, -35. I. Always minus the second one. Always minus the second component. +15 minus 0. J. Plus +15 minus 0, K. Almost couldn't talk. So what are we talking about? -40 in the I direction, -15 in the J direction, +15 in the K direction. Depending on how you did this, you may have gotten a slightly different one with an opposite sign. Okay, but they're still going to be parallel. They're still going to be perpendicular to the plane you started with. Okay? Any non-zero scalar multiple of this vector would still be perpendicular to that plane that you started with. So we can multiply this by any number and it would not affect the direction, right? We would either be parallel or bigger. That's the only two things we can do with scalar multiples. Finding the area. Now this should be really easy. The area of PQR is 1/2 the size of this vector. ugly numbers again, right? So that's 1/2, 1600, 225, 225, 1/2 root 2050, which is approximately 22.638. Okay, again, the exact answer is preferable, just like on the last slide. I don't really care if you have a calculator to simplify it. As long as you have the right answer with the right root, we're good. All right, let's move on to another application. We can find the volume of a really cool word of a parallelepiped. $5 word if I ever saw one. Parallelepiped. What are we talking about? It's like a 3D parallelogram. That's the real basic definition. We're going to draw one. So I kind of think I'm drawing a cube, but picture a slanted cube, okay? I don't know. It's supposed to be slanted. I think it's pretty good for my level of art sophistication. So what we have here is a parallelepiped. It can be defined by 3 different vectors, right? So we have a vector going off in this direction, a vector going off in this direction, the sorts of parallelograms we were talking about in the last slide, but now we also have a vector going off in the back direction, the 3D direction. Okay, maybe you see it as forward. I don't know how. All right, so how do we get the volume of a 3D shape? This might be new news to you, depending on how you studied 3D geometry, or if you did. The volume of a 3D shape is the area of the base times the height of the whole picture. Okay, area of the base. Easy peasy now. The area of the base, if you're following me, the base is this parallelogram down here. So that base should just be the magnitude of B cross C. And again, it really doesn't matter if you did the other order, because, one more time, a magnitude is going to ignore that you did the ordering there. The cross product does care about the order, but the magnitude doesn't. And now you might say, like, well, what the heck are you talking about with height? So with height, we're trying to say, well, how tall is it to drop an altitude from the top of that parallelogram to the base? From the top of that parallelogram to the base. So I want to get something that's perpendicular to both B and C. It's got to be perpendicular to B's vector and C's vector. So what we're talking about is looking at this angle in the top corner as theta. Now, if that was theta, it looks like what we want is the adjacent side. So bear with me here. The height would be the magnitude of A times the cosine of theta. Traditional trig here. If that red side is what we're looking for, then we want cosine, because that's the adjacent. We don't want sine. Sine would be down here. I don't want that. Okay. Now, when do we multiply 2 magnitudes times the cosine of an angle? When do we multiply 2 magnitudes times the cosine of an angle? This would be the absolute value of A dot B cross C. The dot product is when we have the cosine of the angle. So this is really super cool. I don't know. It's something we call the triple product. So we're going to take the A vector and we're going to multiply it by the cross product. The triple product, you can just do the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. So this is one other meaning of a 3x3 determinant that you will use in this course. If I want to find the volume of a generic cough, cough, cough rectangular 3x3 shape, I'm not saying it's a rectangular box, but it's rectangular-like. What we would use is this triple product, which is just the 3x3 determinant we're already so in love with. So find the volume of the, I'm going to say it one more time, parallelepiped given by A I plus J, B J plus K, and C I plus J plus K. Option 1. The slow way, you would do B cross C, and then you would take that with the dot product of A. It wouldn't be that bad. It is time consuming and it's a little silly because we have a much nicer formula, method 2. If you're having extra time on your hands, you could try method 1 and see if you make sure you can get the same answer. Maybe I'll do it after I try out method 2. I don't know. So I have 1, 1, 0. That's the A vector. 0, 1, 1. That's the B vector. And 1, 1, 0. Sorry, 1, 1, 1 as my C vector. So that's 1 times 1 minus 1 plus, minus 1 times 0 minus 1 plus 0 times 0 minus 1. Anytime you have a 0 in that top row, you could just ignore that whole component, right? It's going to be 0 times some number. So what we're getting here is just 1. That's the size of this parallelepiped. It's a unit parallelepiped. I guess I have time on my hands. I'll see how long this video is. Maybe this won't make it in. But B cross C by itself would be I, J, K. B is 0, 1, 1. C is 1, 1, 1. So that's 1 minus 1 in the I direction, minus 0 minus 1 in the J direction, plus 0 minus 1 in the K direction. So that's J minus K. And now we're supposed to do the dot product, A dot J minus K, which is, if I write it out in component notation, sometimes that's easier for me. I don't know about you. 1, 1, 0 dot 0, 1, negative 1. That's 0 plus 1 plus 0, also 1. Ta-da. One more application. Talk about another physics application here is torque. So torque, I don't know, is best described to me as the force used to drive in screws, or bolts. Bolts with a T and an S. So if I have a wrench, I'm going to use my wrench to drive in some sort of nut right here. Right? That's a nut. I'm going to screw in this nut by applying a force against the handle, and that force happens at a radius away from the nut itself. And how does that drive the bolt in? It would drive the bolt in along a perpendicular direction. So that would actually drive my bolt into the screen, because my torque is a vector, and it's the radius vector cross product with the force vector. And if you follow the right hand rule, it should go into the page. So, example, given a 0.25 meter long wrench and a 40 Newton force applied on the wrench at an angle of 75 degrees. Find the magnitude of the torque, which again you can think of as the force driving the nut, driving the bolt in. So again, you know the angle here. If you know the angle, please feel free to use this formula. Torque equals the magnitude of the force times the magnitude of the radius times the sine of the angle, which in this case would be 40 newtons times the radius 0.25 times the sine of 75, 30 degrees. Make sure you're dirty. Make sure you're in degrees before you calculate this. 9.659 what is it? Newton meters, I think. Newton meters for torque. Okay. Well, I hope that was enlightening. That's just an application. Again, I'm just trying to show you where these things come up in the physical world. Obviously parallelograms aren't really coming up too much in the physical world, but again, a lot of the techniques we're using in chapter 16 will help to understand how to find the volume of a parallelepiped. And in chapter 15 even, it'll help to find out how we're going to find the area of a parallelogram. And now, if you ever wanted to help out with a home improvement project, you could calculate the torque. So that's another good application of the cross product. Thanks for watching. I'll see you in the next one where we'll start talking about section 12.5. Have a nice night. Bye.